Hello world. Okay, I'll try to be gentle on the board when I write. So we're going to take a look at a few homework problems, and requests came up for problems 3 and 4. I'm in the wrong section. Oh, it switched me over to the sample exam. Yeah, in my open math, you can't open up 2 different assessments at once in the same browser session, otherwise it gets confused. So I have to go back into here. Okay, here we go. All right. Find the exact slope of the tangent line. Okay, we did one like this the other day. Let's do it again today. The parametric curve. Anybody know what shape this is going to be when we graph it? 2 cosine, 5 sine. It'd be an ellipse. Yeah, if they were the same number, it'd be a circle. Different numbers makes an ellipse. So this is going to be stretched out more so in the y. So the major axis will be vertical here today. All right, so 2 and 5. Let's do it. So we have, oh man, it slipped again. Damn you. Okay, looks like I gotta sit over here today. Darn it. Other magic pen. Gotta love technology. Duct tape. Yeah, I guess I could get some duct tape. String it from the, yeah, use some duct tape and gravity to hold it in place. Okay, so we have x equals 2 cosine of t. And y equals 5 sine of t, and we want to find the slope of the tangent when t is equal to pi over 6. 90% sure that's what it said. Yep. All right. So it's a good idea to look at it and hope you can recognize it, and then you should double check with the graphing utility. So I'm going to go over to Desmos, and Geogebra can do this. Sometimes I like Geogebra better, sometimes I like Desmos better. Stick with Desmos since we've been using it. So I want 2 cosine of t, comma 5 sine of t. And it says, hey, let's let t go to 1, but we know we need a complete revolution, which is 2 pi. So the semi-major axis is 5, that's vertical this time, and the minor axis, semi-minor axis is 2, distance from the center. And we are curious about the point when t is pi over 6. So the only way to graph that point is to say, hey, show me when t is pi over 6. And the point should magically appear there. All right, and we're going to go for the slope at that particular point right there. Yep. Okay. So remember, this isn't polar coordinates. This is rectangular with parameters. So the angle from here to here is not going to be pi over 6. Doesn't necessarily work that way. What else do we need? I guess that's it. We need derivatives. So dx dt, often abbreviated x with a dot on the top, is going to be opposite of 2 sine of t. And dy dt, often abbreviated y with a dot, is 5 cosine. And we just need to evaluate those guys and take their quotient. We want slope, which is dy dx. So that means take your y dot and divide by your x dot. And then we're going to evaluate that at the same time when t is equal to pi over 6. So we're going to get 5 cosine of pi over 6. And then in the bottom, minus 2 sine of pi over 6. All right, Melissa, you got to keep me straight with my trig. I was struggling earlier. Let's see, cosine at pi over 6, I'm pretty sure is the square root of 3 over 2. So that's going to give me 5 square roots of 3 over 2 in the top. And then sine at pi over 6 would then be 1/2. So then I'll get -2 times 1/2, yeah, which will be -1. So yeah, it looks like it's just in the end going to be negative 5 square roots of 3 over 2. Okay. And if we really wanted to, we can take it farther and actually find the tangent line, which is more than this problem asked for. So I'm just going to plug that into my open math. Actually, I kind of want to think about that slope for a minute, so let's calculate it. So I could do that here. What is negative 5 square root of 3 over 2? Desmos says it's about negative 4-ish. And so imagine a line through this point. Does negative 4 seem reasonable? That seems pretty reasonable, doesn't it? Yeah. To actually find the line, we'd have to do a little bit more work. So I think I'll take it a step farther just for fun. So I'm feeling pretty good about it. So I'm just going to go in here and say, all right, I think it's negative 5 times the SQRT of 3, close parentheses, divide by 2. And it gives me this nice pretty print preview. And submit. Yay, I get it right. I want to see that line, so I'm going to take it a step farther. To see the line, I need the point of intersection, which is just right up here. So the x value of that point is going to be 2 cosine of pi over 6, which would be square root of 3. And the y value is going to be 5 sine of pi over 6, which should just be 5 halves, or 2.5. Call it 2.5. And then I could use the point slope form of a line to get a quick version of it here. And that says take y minus your y value, 2.5, set that equal to your slope, negative 5 square root of 3 over 2, parentheses, x minus your x value. And I can just plug that exactly like that into Desmos, and it'll graph that line. So I'm pretty sure that's the tangent line at the point when t is pi over 6. So I'm going to enter that in here. So let's see, I want y minus 2.5 equals negative 5 square roots of 3 over 2 times x minus, minus the SQRT of 3. Ooh, that's beautiful. Look at that sucker. Sits just where I want it. Oops, extra parentheses. Nice. Zoom in here just to double check. It's not a secant line, but it is a tangent line. Yeah, I'm pretty sure that's a tangent, not a secant, meaning it only has one point of intersection in that region. All right, that was exciting. Let's try another. Oh, and I promised to do one like 4 in class yesterday, but I didn't quite finish it. I must have got distracted. Imagine that. All right, so on this one right here, we want to find the horizontal velocity, the vertical velocity, and the speed, which is none of those are slope, right? We need the horizontal velocity and the vertical velocity to find slope, right? If you divide those, you get slope. Anybody remember how to get speed out of those things? Oh, Melissa, you got it. Yeah. Pythagorean Theorem. Yeah, it's the Pythagorean Theorem. Yeah, we take the vertical speed and the horizontal speed, put them together, that gives us the slant speed. Yeah, so this is our x dot, this is our y dot. If we square those guys, add them up and take the square root, that's the speed along the curve there. Yeah, so let's do that. So we'll have to graph this thing right here and see what it looks like. Because I have no idea what that looks like off the top of my head. So we have x is 4, to blow that out for the studio audience. X is 4t squared plus 4t, y is 2t squared plus t. And we want to take a look at this when t equals 3. So I'm going to consult Geogebra. Let's see, I'll consult Desmos for this, I think. Actually, no, I'm going to make Desmos or Geogebra do this instead. Let's get a new plot here. I haven't used Geogebra much lately. No, I want to start Geogebra. In Geogebra, you can't do a point directory. You use what's called the curve function. And it wants to know what's your x expression, what's your y expression, what's your parameter, where do you want your parameter to start, where do you want your parameter to end. So it's just a different way of going about it. So I'm going to do the, curve function. Okay, so my x was 4 times t squared plus 4t, right? Plus 4t, everything's plus, yep. And then comma, my y was 2 times t squared plus 2, comma, my parameter is t, and I think I'll let it go from 0 to 5. Is it typing all that? Oops, I messed up. I missed a comma. Oh, and there's my curve right there. Cool. And then one cool thing I can do here is I can put a point on that curve. Ooh, I almost got to that 3. And then I can move that point around. And the point is remaining on the curve, which is kind of nice. Oh, I can get it to snap to grid. Oh, I kind of missed there. Usually snaps to grid pretty nice. Other cool thing Geogebra has, it has features like give me a tangent line. And down here, it usually gives instructions on how to get the tangent. Oops, usually pop up on the screen better. To use the tangent line, I think I just need a point and a curve. So if I click here and there, ooh, there's the tangent line. And so then I can grab it and move it around, which is kind of fun. And it even gives me an equation, but it's only an approximation in the equation here, right? So anyway, Geogebra has a few more features, but it's a little harder to use. Okay, so let's do the math. So we have, again, x is equal to 4t squared plus 4t. Y is equal to 2t plus 2 squared. Yep, thank you. And then the horizontal speed is just x dot. And so that's going to be 8t plus 4. And the vertical speed is just going to be y dot. And that is going to be 4t. Yeah. Now here they only ask us about t equals 3. So I don't really have to do it in general. So my horizontal speed, so x dot evaluated at 3 would be what, 24, and 4 is 28. And then y dot evaluated at 3 would be just 12. And then the speed in parameterizations involves the Pythagorean theorem. Speed is x dot squared plus y dot squared, square root of all that. So that's going to give us 28 squared plus 12 squared inside of a square root. And were we asked for exact? And generally on these problems, if it doesn't say exact, then an approximation is okay. But I'm not sure about that. Usually that's true. So cleaning that sucker up, what do we get? 28 squared plus 12 squared is 928. So we want the square root of 928. Which is approximately what? Let's see. SQT of all that, 30.463-ish. Usually if I'm worried about accuracy, I take it out to 4 places in the program, and I usually do all right. So 30.4631, let's say. Oops, where's my notebook? All right, and sometimes I can plug in something like the square root of 928. So let's see what this one accepts. Horizontal we found was 28. Vertical we found was 12. And then I'm just kind of curious, will it accept the SQRT of 928? Was that what it was? 928. zoom out a little bit. And it's also giving me the approximation here. Submit. It liked all three. Cool. All right. I wonder if it would like that approximation. 6. What's that? Less picky than MyMathLab. It depends on how somebody wrote the question. But yeah, I do find MyMathLab to be a little pickier. You what? In here or MyMathLab? MyMathLab, yeah. Every system's a little bit different. Was that what we found? 4631? Does that look right? Okay, so if I hit submit, it liked that too. Cool. Wonder if I can get rid of the 1 and check it. Oh, I only get 2 tries, and then I have to, it regenerates the numbers. Yeah. Okay, well, that was fun and exciting. All right, how you guys feeling about parametric calculus? Not too bad. Okay, so shall we take a short break for a video? Excellent. So I'm going to show you a little something I made earlier today. So has anybody ever played around with drawing curves in a program designed for making shapes like Illustrator? So there's different types of curve. A common type of curve for making shapes in a 3D drawing program, like when a professional designer sits down in a computer and draws out some funky shape, they're not necessarily freehand drawing. They're using tools to make the curves nice. And those cool tools generally depend on cubics. So something to the 3rd power. So here's the reason we do cubics. If with just a line, we have slope. With a parabola, we have slope and we have concavity. So connecting 2 parabolas together, you can get their slopes to match and their concavity to match. Okay. With a cubic, though, that gives you just a little bit more ability to get that point of intersection to look good, so it's not clunky. And as you start getting higher than a cubic, they get way too hard to work with. So cubics are a nice balance. And there's a few different types of cubic functions people use to make graphical designs. One is called a Bezier curve, and the other more general type of curve is called a cubic spline. Okay, and it's just connecting points together with little chunks of cubic functions. Now, usually what we do is we parameterize them. So what I did is I went into Geogebra and I typed up the parameterization of a cubic function that connected these 2 points together. On the endpoints, this point B right here, that's the tangent line from A, and then this C right here is an endpoint for the tangent line for D. But it's more than that, because the distance also affects how far it makes the curve stretch out. Okay, so if I tried to hold DC at the same slope all the time, I still have the same tangent at that point. I'm just stretching this point right here. Okay, and so I built this curve just by playing around. And so this isn't quite the way they work in a 3D graphics program. I'll show a video on how it works in a 3D graphics program. But this is how curves are designed. And I can totally move them so they're on other sides. Okay. And so the cool thing is, suppose I needed this curve for some figure I was designing. Maybe it's part of a boat. Maybe it's part of a letter. Maybe I'm designing my own font. Who knows? Could be anything. All I need to get this shape right here are 1, 2, 3, 4 points, instead of a gazillion points on here to try and make it happen. So these curves were designed because we had to figure out how to have computers help us do that and how to store it in the most efficient way possible. Okay, so with 4 points, that's all the computer needs to remember. Those 4 points, it can reproduce this curve beautifully. The other thing is it can scale it up and shrink it down perfectly every time. Just a picture to kind of illustrate. Too many connections. Oh, interesting. Oh no, does that mean other people are interfering with my MyOpenMath? Uh-oh, they better get bigger servers. Oh, okay, I can get there a different way. Let's go to, what's it called? It's not community calculus. What's the name of our book again? Contemporary calculus, okay. Contemporary calculus. I just want to show you some pictures from our book here. If I can find the right chapters, Dale's website, Dale's book. All right, I want 9.4.5 Bezier curves. All right, so here he's got an illustration of what I'm talking about. Blow that up a bit. When you zoom in on a lot of computer images, it starts to pixelate. Have you seen that before, zooming in and out of images? So cubic splines, Bezier curves, they're all part of a bigger thing called vector graphics. And vector graphics, instead of using points to remember what something looks like, they use mathematical equations, like this crazy stuff I have here in Geogebra. Okay, so the computer has just this stored in there, and all it has to do is say, okay, tell me what A, B, C, and D are, and bang, there's the curve. It just whips it out really fast. So the idea of Bezier curves or vector graphics is you only really need a few points on the curve, and then you use math to connect them smoothly. So the amount of information you have to store is pretty minimal. Okay. And then on the next page, he goes on to talk more about, here's a linearization between 2 points. We did that the other day in class at the beginning of the week. Bezier curves were developed in the 1960s. And then he gives, this is the equation for a Bezier curve with 2 points and 2 handles. And the handles allow you to change how that curve works. And I found a really cute video about that. And I posted it in my Open Math, but wow, that's a first. This has never happened before. It's good and bad. It means my Open Math is getting popular, but it's bad because I can't use it right now. Bezier, and I keep mispronouncing it. It's Bezier, but you know, being an American, I always want to throw that darn R in there. Bezier curve. Okay, so there was a cute video. Oh, where was it? Animated Bezier curve, was it this one? No, oh, this is not a bad one, yeah. Okay, so check out this animation right here in the middle. This isn't the video I wanted, but it'll work. So this is a system like the one I have. We have our endpoints for the curve, and we have our handle points related to the tangent from that endpoint. The way Bezier curves work with computers is then we have this other point that tracks along on this line. We have this other point that tracks along on the connection between the handles, and we have this final point that connects there. There's then another point you put on those intermediate lines, and what the connection between those two does, that's the tangent line of any point on the curve, which is kind of cool. And so what the computer does is, given those 3 points and the parameterization, it just tracks that tangent line and traces the point. So imagine that red point on this green line is a pen, and that's how the computer draws the curve based on 1, 2, 3, 4 points. So all it needs is this little tiny program that says, here are the, given the points, make this line, this line, this line, makes 5 lines, and then it tracks that 1 point on the center line, and that traces the curve out. Okay, so you can see it's basically a mechanical system based on only 4 points. And based on that, you can draw just about any curve you want. And all you need is a few points to make that happen. And what designers do is they just manipulate the endpoints and the handles to make the shape flow the way they want it to do. Okay, which is kind of fun. And so here they just have a more complicated curve with some other handles on it. So you can put as many handles in between as you want. The most basic one has to have, it should have 2 handles in between. You can get away with 1 in between. Then you get this kind of quadratic type shape here. But the cubic just gives you a lot more versatility in 3-dimensional space, which is kind of fun. And so I had a really cute video in my Open Math where oh, there it is, okay, where this guy walks us through it. So just if you have some free time later, I'd highly recommend in section 9.4, check out what I call the interesting video. It's a designer who also knows some math. It looks like he wrote it up in Geogebra, showing step by step how this is all working right here. So I think I think that's enough for that right now. We have two options. We can stop here and you guys can do homework, or we can get a jump start on Conic Sections, which is section 5. Today it's a democracy. What do you think? You gonna go and do homework, or should we get a jump start? Okay, jump start it is. So we're gonna get a jump start in section 5. That's not gonna change at all the calendar. So that's a cool animation they made right there. And somewhere in Geogebra, I actually built this one with all those curves, but I couldn't find it. So I had taken this a step farther by plotting the points on each of these, and then the points to show how the tangent traces out the curve. But anyway, I'll post this if anybody wants to play with it. But it's just kind of fun. You can totally make any kind of curve you want. So I did I had a group of students who took 111, 112 fall, winter, and they had nothing to do in the spring because calculus wasn't started. So we did a third term where we did basically the stuff we're doing here, but without calculus. And their assignment was to make curves like this and design a letter with them, which was kind of fun. But these are the kind of curves that are used to design just about anything that you see on a computer these days. Okay, so the last two sections in this chapter are what are called conic sections, and so I'll explain more about conic sections in a second. The first part tells you just the basics. You've probably seen this in other courses, so this is mostly a review of stuff you had in an algebra course before. Section 6 takes it a step farther by going over some physical properties of conic sections, in particular, how to do polar conic sections, which is kind of neat. And I'll explain why polar conic sections are important next week. I don't think I'll get to that today. So just a quick review on conic sections and we'll call it a day. I gotta sit down. All right, fine. Conic sections. So there's a couple of different ways to generate conic sections. One way is, and I need an illustration that's better than I can draw. Images. Okay, they're slices of a cone. So if you slice through a cone perpendicular to the major axis of the cone, you get a circle. If you slice at an angle that is between perpendicular and the angle of the edge of the cone, then you get an ellipse. If you slice through at the same angle as the edge of the cone, you end up with a parabola. And if you slice somewhere between the angle of the edge of the cone and vertical, you get a hyperbola. Okay. And in case you don't remember those shapes, I'm sure you remember circles, ellipses, and parabolas quite well, but hyperbolas aren't as popular. So I'll just, I can't stand up. So reminder, standard ones, we have the idea of a circle. In rectangular coordinates, that's something like x squared plus y squared equals 1. We have the parabola. Things like y equals x squared or x equals y squared. So circle, parabola, something like that. Ellipse. Now, sometimes we use the word oval when we're talking about shapes. Oval is kind of a pretty generic term. Ellipse is a kind of oval, but there are many curves that are oval-like that aren't ellipses. Okay. So an ellipse would be something like x squared over 4 plus y squared over 9 equals 1. And so that one would be kind of elongated vertically. And then hyperbolas come in a couple of different forms. Hyperbola. The most basic hyperbola that you've seen before is y equals 1 over x. And that's where we have this curve that's asymptotic in two directions, vertical and horizontal. And there's usually a mirror image through some point of that thing. And so hyperbolas always have asymptotes. But circles, parabolas, and ellipses do not have asymptotes. Another example would be something like x squared minus y squared equals 1. That would also yield a hyperbola. So I'm going to graph that one in a program just to take a peek at it. Let's look up Desmos, for example. Squared minus y squared equals 1. And so there's that hyperbola there. The asymptotes are sometimes easy to find and sometimes not. This one's pretty straightforward. If you consider the line y equals x, we'll see that's one of our asymptotes, and the other asymptote is y equals negative x. If I were to tweak this, kind of like the idea of an ellipse, and say, let's take x squared divided by 4 and y squared divided by 9, then my asymptotes have changed, and I need to kind of figure out where they went. And so I'm just going to do an example of that here. So let's pick on this guy in a new page. So I had, I think it was x squared over 4 minus y squared over 9 equals 1. And I'm going to get a snapshot of its graph. And then we'll identify the asymptotes. That should be enough. Right there, maybe. So kind of like a hyperbola, an ellipse, we have a semi-major and a semi-minor axis. The 9 came from a 3 squared, and the 4 came from a 2 squared. And so if I go up 1, 2, 3 in a vertical direction, and I go right 1, 2 horizontally, I can make this box. And then, let's say I have a line tool somewhere here. I thought it was hiding right there. Yes, there you are. Give me a line. And if I draw a line for this box here, that's going to demonstrate my asymptotes. So I want to try and head through the corner of that box. I think that's kind of right there. So here, if you look at the box, we can see the box has a rise of 3 and a run of 2. So it looks like y equals 3/2 x and y equals negative 3/2 x should be my asymptotes. And these, since they're not vertical or horizontal, are called slant asymptotes. Does anybody remember another name instead of slant that's sometimes used? Starts with an O. Sometimes they're called oblique asymptotes. So you'll see that sometimes too, oblique asymptote. So one way to generate them is from a cone. Now it's kind of a problem to take a 3-dimensional cone and slice it to come up with your 2-dimensional object. So it turns out there's other interesting properties of these objects. So I'll graph those in the graphing program first, and I'll tell you a couple of properties. So over the next few days, we're just going to analyze their properties and then push over into polar coordinates. So y equals 3/2 x. So here we can see that asymptote. And if I zoom out on this sucker, you know, the farther you zoom out, the function starts to look like those lines. Because remember, asymptotes represent big picture behavior, right? As x goes to infinity and y goes to infinity. So you can hardly tell the difference between them when you zoom out. All right, so other properties, you're probably familiar with conic sections, and then I'll show you some you might not be. How does one define a circle? Say a whole bunch of points, makes this cute curve. Is there anything special about all those points? Yeah, they have a radius. They're all the same distance from the center. So the circle is the set of points equidistant from some central point. And it turns out all of the other conic sections have a similar definition. They're related to some distance from some place. Okay? Often with the other conic sections, we have some kind of focal point, and we have a line called a directrix. So we have a point usually called some kind of focus and a line called a directrix. Directrix. And so a parabola, for example, can be defined similar to a circle. Parabola. It's the set of all points equidistant from a focal point and a line. Huh? What the hell does that mean? I'll show you in a picture. So I have to have some line. So let's say I have this horizontal line here. That's my directrix. And then I have to have some focal point outside of that line. So that's going to be my focal point. Let's call that F. And my parabola, well, can you imagine that right in between here, there's a point right in the middle, right? And it's got the same distance from that point P to here as it does to the line, okay? That's going to end up being the vertex of my parabola. Now later on, there's going to be other points, like there's going to be a point over here somewhere, such that this distance right here is identical to that distance right there, that they match. And if we collect all of those points, so somewhere up here, there's going to be another point such that these two distances match, that is going to lead to a parabola. Okay. So what we'll do is next class, we'll actually take that definition, we'll pick a line for the directrix, we'll pick a point for the focus, and we'll see if we can use this definition to come up with the equation of the parabola that has that particular directrix and focal point. Okay. Who cares about the directrix and the focal point? Like, the hell are you wasting my time on this for? Here's the reason that matters, and it's kind of because of this right here. So imagine this line going straight through. Okay. And way out in space, there's this satellite. And it's sending a signal. Well, that signal is going to follow this line, and it's going to hit this parabola. Turns out, the way these two lines come in and out there, if you imagine the tangent line over here, this angle right here matches that angle right there. And so anything that heads straight into this parabolic, maybe it's a dish, gets reflected into the focal point. So did anybody ever have dish TV? Or you've seen them all over the place. There's this little dish, and there's this little lever hanging, and with this little receiver floating above the dish. That receiver has to be pretty darn close to the focal point, so that anything that heads into that parabolic dish gets reflected into that focal point. So if we made a pool table that was a parabolic shape, and we hit stuff straight ahead. It's got to be straight down like this. And there was a hole on the pool table at the focal point. Every ball hit straight down would reflect into that hole. Now the problem with that is you have to go straight down. Okay, that's when another shape comes in called the ellipse. And oh, we're out of time. An ellipse has two focal points, and it has another line out here called the directrix. Okay, it's not related the same way as the parabola. Cool thing about an ellipse is if you pick any point on the edge of the ellipse and you imagine its tangent line, and then you connect these points right here, this angle will always match that angle right there. So anybody ever go to the dentist? Yes, okay. So you know how the dentist has this curved mirror hanging above you and he holds it up and it shines at you? So the curve of the dentist mirror is a chunk of an ellipse. The light of the mirror is located at this focal point. They adjust the mirror so that your mouth happens to be the other focal point. And so he gets maximum light into your mouth using that, which is kind of neat. If you made a room that was elliptical shaped and you stood here and whispered, somebody else here could hear your whisper as if they were standing right next to you. Should be pretty crazy. Yeah. In the, I think it's the George Bush Airport in Texas, there's a dome in the middle of this hallway that goes both ways. And I was walking through there one day with a friend and we were chatting. And all of a sudden I noticed my voice was getting louder in my head as I was walking through this dome. And I'm like, how the hell am I getting louder in my head? This is so weird. And I did some research. It turns out that the dome above me was a parabolic dome. And about the height of an average person's ear was the focus, so that any sound that projected would then reflect back at that person. So when you were in the middle under the dome, you got louder, which was kind of cool, which blew me away. So there's all kinds of uses for these kinds of things. So we're just going to study these reflective properties, and then we're going to work our way up to planetary orbits are elliptical. And often what we need to do is kind of track some angle that the planet moved from as it's rotating around some central body. So having an ellipse in polar coordinates is quite powerful. So that's what we're going to work up to. And we're only going to do a tiny bit of calculus. Mostly this is just geometry stuff that we're going to do here. All right, that's it. Thanks for letting us jump ahead a little bit. Have fun. Get that homework done soon.